We are going to look at the airfoil nomenclature. We are going to look at what it means by lift and drag forces. We are going to talk about lift, drag, and pressure coefficients and other matters. Of course, the airfoils are not unique to just the wind turbines. They are used in airplane wings. They are used in propellers and turbofans. They are used in helicopter rotors. They are used in compressors and turbines inside engines. Pardon me. They are also used in hydrofoils, which are wing-like devices which lift up a boat, sometimes above a water line. And of course, they are used in wind turbines. They evolved over a period of time. Very early experiments, people thought the airfoil had to be very, very thin and sharp so that it can slice through the air without any kind of resistance or a drag. So they tried to make the airfoils very, very thin. These were made of fabrics. So they thought as it flows through the air, it's going to have limited drag. In reality, what happened was, if you have a small amount of angle of attack, in other words, if you tilt this particular airfoil a little bit, then the velocity vector comes from the bottom. Then the air molecules have to turn around this sharp corner. When they do that, they get separated and stall. So such a sharp leading edge is not so good. So Wright brothers realized that this is not a good case. So Wright brothers, when they were building their airplane in 1903, they did a lot of wind tunnel tests. They took somewhat thicker airfoils with somewhat a blunted leading edge. So that's what they used in their biplane. They were still using fabric-like material, but with somewhat a rounded leading edge. So there were two such airfoils connected by all kind of struts and wires and so forth. By the time the First World War rolled around, people had already recognized that these are not even good airfoils. Plus the biplane configuration was very, very draggy because you had a lot of struts and wires and structures exposed to the air. All of those were causing drag. So they decided to go to a single airfoil, somewhat thicker, so it was internally braced, or all the structural elements were inside the airfoil, making it strong. Of course, in modern wings, you could also put fuel tanks. You can put control systems for rotating flaps, rotating ailerons, and so forth. So this is the evolution over a 44-year period in the technology of airfoils. So early designers mistakenly thought everything should be sharp leading edge. They stalled quickly, therefore things evolved as shown here. Airfoils, to design an airfoil or to define an airfoil, you start with a chord line. So in the beginning, you start with a chord line. It's simply a straight line that you join from the leading edge of an airfoil to the trailing edge of an airfoil. Next thing you do is you add some kind of a flexure to the chord line, deform it if you will. We call that the extra deformation that you have put on as a camber line. If you don't have any camber line, then you have zero camber. Then basically the green line just lies on top of the blue dotted line. After the camber has been added, then we add the thickness, equal amounts above and below, normal to the camber line. So you do this over and over, put them all together. This is how an airfoil looks like. It's a pretty ugly looking airfoil, but you get the idea. So an airfoil is basically a superposition of the chord line, which is only the straight line we have. Then there's a camber line, which is a curved line, and then the thickness, which is a non-uniform. Therefore, the airfoil shape itself is curved. So how do we measure angles and so forth? The only straight line that we have is a chord line. Therefore, that's what we use for measuring what we call the angle of attack. Symmetric airfoils, as I mentioned earlier, will not have any camber line. Therefore, when you add equal amounts of thickness above and below, you'll get a symmetric shape. So that's what you would get. Modern wind turbines tend to have some small amounts of camber. We will see what the reason is at a later time. Okay, now you have the wind coming or approaching an airfoil. The dotted line I have shown is the camber, the chord line. So the angle between the free stream, that's the wind coming towards the airfoil, minus any induced velocity losses. So this is a net wind speed. The angle between that net wind speed and the chord line is called the angle of attack. It's often given a symbol called alpha. Angle of attack is therefore the angle between the free stream and the chord line. In modern wings and also modern helicopter rotors and modern wind turbines, the geometry is highly twisted. So near the root you may have one type of a twist, near the tip you may have another type of a twist. Therefore the angle of attack may vary all the way from the root all the way to the tip. Let's now look at the lift and drag forces acting on a wing section. So here is the airfoil with the chord line. So what happens is lift is primarily caused by pressure forces on the airfoils. Pressure forces are pressure is a force normal to unit area, normal to a surface, in this case the wing surface. So this is the wind stream. So the forces that are caused by the pressure forces, and also there may be viscous forces, these are the ones that gives rise to lift and the drag. The component of aerodynamic force normal to the wind velocity, after we have subtracted off any swirl, any induced velocity, etc., wind velocity vector, normal to that vector is called the lift. L prime is lift per unit span, per foot of span, or per meter of span. The component of aerodynamic force along the free stream per unit length of span is called drag. So this is D prime. We often non-dimensionalize everything in our practice. That's because L prime and D prime are dimensional quantities. They are going to be Newton per meter or pound force per foot of span. So a large chord rotor wind turbine at each section may produce a lot of lift and also have a lot of drag. On the other hand, if you divide it by 1/2 rho velocity square, which is the free stream velocity square times chord, you get a non-dimensional number called CL and also CD. C subscript L is called the lift coefficient, again 2D. C subscript D is called the drag coefficient. So this is how we normally define it. Why do we do that? Because rather than dealing with dimensional quantities that will vary from installation to installation, one windy day to another day, one wind condition to another condition, if you non-dimensionalize it, you can quantify the properties regardless of that day's density, velocity. So you could measure these quantities CL and CD in wind tunnels. It doesn't matter what the rho is or what the V infinity is. We just want to capture the CL and CD information. So when we talk about an entire wing or an entire rotor, we'll be using a L, D, and there'll be a C capital L, C capital D. These are used in the airplane industry. We are not going to use much of C capital L or C capital D in our work. So we will be primarily working on a rotor section or a blade section. So we will use a L prime, which is a Newton per meter, drag prime, which has got a Newton per meter, and the non-dimensional coefficients, lift coefficient and drag coefficient, which are defined earlier. Coming back to what causes lift, we mentioned there are pressure forces acting on it. So these are the pressure forces. Notice that they have a different lengths. So the very long length means high pressure force per unit area or high pressure value per unit area. Very short distance arrow means low pressure. How can we change pressure? Bernoulli equation says pressure energy P over rho plus kinetic energy 1/2 velocity squared is a constant. So the molecules can trade energy between kinetic energy and pressure energy. So near the nose of the body, the flow reaches a stagnation. That means come to a dead rest and slowly accelerating over the body. So it's got a very, very low velocities near the nose. Therefore, the low velocity, according to Bernoulli equation, produces high pressure. Once the molecules accelerate over the surface, they pick up velocity, high velocity, then the low pressure. Somewhat similar thing happens on the lower side. So if we want to compute the lift, all we have to do is integrate it. So let's go to the next slide. Before we integrate, sometimes people will subtract from the pressure, the atmospheric pressure. The difference between the actual pressure and the atmospheric pressure is called gauge pressure. Many pressure gauges measure this. For example, when you measure the pressure in your tire of your car, you may get a value like 30 psi, 30 pounds per square inch. It's really 30 plus 14.7 psi. 14.7 is atmospheric pressure outside the tire. Inside the tire, it may be 44.7 psi. So the difference is 30 psi. So once you subtract the P minus P infinity, notice that some of the vectors are pointing towards the surface because there P is greater than the atmospheric pressure, so it's positive. Other arrows are pointing away because P minus P infinity is negative. Pressure is not negative, but the pressure is less than the atmospheric pressure. So here we have very, very low pressure, very low pressure. So low pressure, in this case, pointing as an arrow upwards, suctions or sucks the surface, pulls it upwards. So this is what produces the lift. Essentially, the difference between the pressure above and below can cause the force upwards or, so of course, downwards also. So P minus P infinity is called the gauge pressure. It will be negative over some portion of the airfoil, especially the upper surface. That's because the velocity there is very high and the pressure can fall below the atmospheric pressure. Now, once we have the pressure values that we just talked about, gauge pressure, we can integrate the pressure forces all the way from the leading edge to trailing edge. Basically, integrate the pressure on the lower side per unit span. So you could think of it as a dx times 1. Dx is in meter, 1 is in meter. So this is meter squared. Pressure force is Newton per meter squared. So when you multiply it, you get Newton forces. Same way on the upper side, you get some lift. So you take the difference between the forces pushing the airfoil up from the bottom and down from the top. The difference is the net force on the airfoil that produces the lift. So we could group these two terms together, and you could write it as follows, as shown here. You can also subtract atmospheric pressure from the pressure. Nothing changes. So it's P infinity, we can subtract it. This is the gauge pressure integrated from the leading edge to the trailing edge. This is the lift per unit span, Newton per meter, or pound force per foot of span. If you now divide the left side and right side by 1/2 rho V infinity squared C, this 1/2 rho V infinity squared C is called a dynamic pressure. We are going to divide these things by dynamic pressure, these things by dynamic pressure. We are going to divide X over C by dynamic pressure. On the left hand side also, we are going to divide this L prime by this number. As we saw earlier, then you'll get a lift coefficient on the left hand side. So we get lift coefficient on the left hand side, which is CL. These are called CP, which is the pressure coefficient, again non-dimensional. So the pressure coefficient is P minus P infinity, which is the gauge pressure, divided by 1/2 rho V infinity squared, which is the dynamic pressure. So The lift coefficient is simply the pressure coefficient integrated. Notice that there is no dimensions here at all. That means if you measure the CP in one wind tunnel versus another wind tunnel, as long as we are talking about the same airfoil, same angle of attack, you would expect to get the same non-dimensional values. Although dimensional density and the tunnel velocity may be very different. So non-dimensional, 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 you get a non-dimensional answer. So why do we use CL, CP, etc.? Why don't we directly use lift force, lift per unit force, etc.? Well, let's say you have a big wind turbine section. You have a small wind turbine section that you want to model in a wind tunnel. Obviously, it's much cheaper to do this one on the left side than this side because the small models cost less to build, less expensive to manufacture or buy. They fit into very small wind tunnels in the wind tunnel very quickly, nicely, easily. This may not fit in a wind tunnel. So if they are, as long as they are geometrically similar, that means they have the same body shape, non-dimensional form. One is used in a wind tunnel, other one is used on an actual wing or on an actual wind turbine. They are operating in different environments. This is in a small wind tunnel. Let's say it's at sea level. This is at velocity, let's say it's only 10 meters per second. This is operating on a wind turbine. The velocity, let's say, is 7 meters per second. So velocity has changed. Density may have changed depending on the altitude of the terrain and how tall the tower is. So although L prime and D prime, etc. change, dimensional quantities change, the CL, CD, and CP remain identical. So if they are geometrically alike, if they operate at the same angle of attack, there's a quantity called Mach number, which is the speed of the flow divided by the speed of sound. This is going to be very, very low for our low speed, slow spinning wind turbines with low wind speeds. So we are going to assume that the Mach number is 0. Then a quantity called Reynolds number. Reynolds number you may have seen in your previous studies in aerodynamics and also in mechanical engineering. It's a density times velocity times the chord divided by viscosity. So the numerator is density times velocity times chord, deals with the inertial forces acting on the body, in this case the airfoil. The mu in the denominator is a measure of the viscous forces. So the ratio between the inertial forces and the viscous forces is called Reynolds number. So coming back, a small airfoil tested in the wind tunnel and a large airfoil used on an actual rotor or on a wing will have identical non-dimensional coefficients CL, CD, and CP if they are geometrically alike, operate at the same angle of attack, 0 Mach number in our case, and same Reynolds number. This allows the designers and engineers to build and test small models which are less expensive and compute the quantitative numbers CL, CD, and CP. It's also qualitatively, you can visualize the flow, see when does it stall, where does the flow become turbulent, and all kind of good stuff. So the geometry must be identical, the Reynolds number must be identical, angle of attack must be identical. Mach number in this case is not important, but for compressible flow, the Mach number must be identical. Then the behavior of CP, CL, CD will all be the same. Even in a full-size airplane, full-size wing, full-size rotor, this follows. So if you want to find the force on a rotor disc, rather than computing it dimensionally or measuring it dimensionally, you can make a small model and measure it and non-dimensionalize it. How does the CL behave at the angle of attack? It can be shown that initially it follows a nice linear behavior. The point where it crosses the x-axis is where the lift goes to 0. So that point is called 0 angle of attack, or let's say alpha naught, alpha subscript 0. So the slope of this curve tends to be roughly 2 pi if the angle of attack alpha is in radians. So many airfoils have nearly identical slope. Of course, this crossover point is called the angle of zero lift, or alpha 0. All good things must come to an end. So if you keep on pitching an airfoil up and up, eventually the airfoil will stall. So this is a viscous loss of lift. We don't want to operate in this region for our wind turbine because, as we mentioned earlier, we want a lot of lift. We don't want less lift. We want a low drag. We don't want a high drag. Stall also increases the drag. So lift is low, drag is high. So we stay away from such regions. So we will primarily be operating in this region for our wind turbine. So that's called the stall behavior. So let's say you change the camber of an airfoil, then the behavior will somewhat be similar, but will also be different. So this is what you would expect for a cambered airfoil. But if an airfoil is symmetric, that means it's got the same upper surface shape as well as a lower surface shape, then at zero angle of attack, the flow is parallel to the chord line. So what happens on the upper surface is also happening on the lower surface. So the curve looks like this. So adding a camber produces some improved lift. So sometimes this is often used in wind turbine industry to generate much wanted high value of lift. But adding a lot of camber can also cause the airfoil to stall sooner perhaps. It can also cause very large pitching moments. Those are the twisting moments that the airfoil experiences because of the pressure distribution being uneven along the chord. So mathematical model for the straight line that I just showed is CL equal to 2 pi times alpha minus alpha 0. When angle of attack equals alpha 0, CL is 0. Therefore, this is called the angle of zero lift. For symmetric airfoils, alpha 0 is 0. How about drag? It's caused by different mechanisms. It's caused by viscosity. So as the air molecules flow over the surface, and some of the molecules are sticking to the surface, others are moving past it. So there is a force exerted by the stationary molecules on the moving molecules and vice versa. So the stationary molecules drag the moving molecules back, and the moving molecules likewise try to push the airfoil back. So this causes one source of drag is called the skin friction. You may also get a pressure drag if you get a lot of pressure in the nose part of the airfoil upstream and a very low pressure in the back end of it. The pressure difference can also produce a drag. This is called a pressure drag. So third source is the shock wave formation producing wave drag. We are not going to be looking at it in our work. So coming back to the skin friction, if you're sitting on an airfoil, you'll see molecules moving past you. But you'll see the next layer is going a little bit slower. Next layer is going even slower. The last layer is stuck on the surface. So this profile is called a velocity profile or a boundary layer profile. I have exaggerated it as the size of it. It'll be very, very thin. It'll be like a millimeter for 1 meter of chord. So the moving molecules want to pull the airfoil backwards. So that's what causes a shear force or a viscous force that causes the drag. Here's another place where we are showing the boundary layer. Now if you have a nice smooth flow, which is called a laminar flow, layer by layer, you'll get a velocity profile that looks like this. This is slope of this line, which is this velocity by 0 by distance. You could think of it as this angle, if you will. Slope is small, so the drag force is small. Newton said the shear stress or the tangential stress is proportional to viscosity times this particular slope. Slope is this angle, which is this distance by this distance. In laminar flow, you get nice orderly flow like this. So on the surface you get drag, but in this case it's not so bad because it's a laminar flow. How does the flow slow down? How does the molecules know what's happening to the neighbor molecules? In liquids, it happens because of intermolecular forces. Basically the protons on one molecule are pulled by the electron cloud surrounding the neighborhood molecule. So if this molecule moves, then that electrical force, attractive force, wants to pull these molecules, and this pulls the plate backwards. In gases, you don't have such intermolecular forces, very strong forces, because the molecules are far apart. So rather, the diffusion of molecules. The slow moving molecules from here may migrate and go in here. Likewise, the high moving molecules may migrate down here. So this is the mixing that causes the velocity to be smooth. So eventually you get some kind of a velocity gradient, molecules randomly migrating up and down. This is called a diffusion. It's a very slow process, so it's not a very powerful process either. So drag per unit area, which is proportional to the slope of the velocity profile at the wall, is somewhat low in laminar flow. That's why we like laminar airfoils, laminar flow over airfoils, both for wind turbines and also for aircraft and compressors and turbines and anything else. In turbulent flow, you don't have such orderly flow. You have molecules randomly moving about, swirling about in 3 dimensions, x, y, and z. They are also changing its path from time to time to time. So if you release a particle here, it may go this path. You could release another particle very close by. Just a few seconds later, it may take a totally different path. Another particle may take a different path. So we can't tell what's going on just by looking at the instantaneous picture. So what you do is you take a time average. For example, you can put a velocity probe here, measure the velocity every millisecond, take 1,000 samples over 1 second, average it. That's an average velocity. So this is called a time averaging. So if you do a time averaging, then you'll get a nice orderly picture like before. This is the time average streamlines. Notice that now the slope is almost 90 degrees. It's very, very high. That's because the turbulent flow mixes the fluid layers very, very well. High velocity molecules are brought very close to the surface by those eddies, swirling current. So likewise, the low velocity molecules are going all the way up there. So we have not quite recovered the free stream velocity yet. So turbulent boundary layers tend to be very, very thick because this velocity gradient is high according to Newton's law, Newton's hypothesis about shear stresses. The shear stress is high, so you get a very, very high drag. So turbulent flow is bad news for airfoils on wind turbines, so we try to avoid turbulent airfoils. In summary, laminar flow will have a low drag, turbulent flow will have a high drag. The region where the flow changes from laminar to turbulent flow is called a transition zone. If we can postpone the transition zone as far back on the airfoil as we can, we'll get the lowest drag. Ideally, the entire flow should be kept laminar.